Okay, let's go ahead and wrap this study guide session up here with the last question set, 30 through 43. See if we can get through this one. 30, this is with a cricket batter here. It says, would the picture above result in a balanced or unbalanced forces? Circle one. Balanced forces mean that the forces, opposing forces are equal and opposite. So in other words, 10 on this side, 10 on this side. In this case, we have 50 on that side and 15 on that side. So it looks like they're not the same, therefore they're called unbalanced forces. What is the net force in the picture above? Well, that's a net force is what's left over after the whole thing happens, right? So I've got 50, the batter's swinging with 50 that direction, and the ball is coming with 15 this direction. Well, which one's stronger? The 50 is. How much stronger? 35 stronger. Which direction? That way. So the net force is going to be 35 newtons in that direction. That will be what's left over, and that's called the net force. 32, what could you do to balance out the forces in the picture above? Well, the pitcher could throw the ball harder with 50 newtons of force, because that would be 50 versus 50. Or the batter could swing the cricket bat with less force, with only 15 newtons of force, because then it would be 15 and 15 meeting, and that would balance them out. How might the motion of the ball change if the batter increased the force to 100 newtons? So if you make that 100 and it hits the ball, now it's not going to send the ball 35 newtons of force in that direction. It's going to send the ball with 85 newtons of force in that direction, which is going to make the ball go in that direction a lot faster. So that the motion of the ball would change. It would speed up in that direction. Okay, 34. Circle the best choice for each option below. Identify which forces are contact and which ones are distance forces. Static electricity. Static is like John Travolta when his finger gets close to the door but not touching the door. So you really, for static, and that's how we pulled the can in NASCAN with the balloon. We pulled it. Did we touch the can in NASCAN? No, that was actually a rule. We couldn't. So static electricity is a distance force. Friction. Well, friction is two opposing forces rubbing together, so it's a contact force. Gravity, I sure hope the moon isn't going to touch the earth. If it does, it would be catastrophic on a cataclysmic scale. So it would be a distance force gravity. It's not touching. Magnetism. Magnets can get close and they don't have to touch and they can still pull. So that's called a distant force. Applied force. Applied is when I actually physically touch something and push it. So that is a contact force. Intention, that's stretching something out like a rubber band. So you actually have to physically stretch it, so that's contact. Well, love waves, especially swimming in them. 35, label the wavelength, amplitude, crest, and trough of the wave above. Let's start with the wavelength. A wavelength is how long a wave is. So we measure a wavelength from the crest of one, or the top of one wave, to the top of another, that distance. So if I were to take and show you on the cursor here, from this point here to that point there, that is one wavelength. Or you can also measure from the bottom of the waves to the bottom of one wavelength. Amplitude is the power of the wave, like how much power it has in it. Think about this in terms of real waves, like an ocean tsunami. What causes an ocean tsunami to be more destructive and have more power? It's the height of it, right? So the height from the median here all the way to the top, that's the amplitude. The crest is the name of the top of the wave up here. That's the crest. Old, dinosaurs, Diplodocus or some other dinosaurs, they had those weird things out of their head. They call those crests. And they actually call the top of a chicken's head, that weird thing that sticks up off a chicken head, the chicken's crest as well, in case you didn't know that. Then the trough. Well, it's the opposite of the crest. The trough is down here. Now, if you think about it, farmers, they throw sludge and slop and food into a trough, and the pigs come and eat it. Well, they eat out of the bottom of one of those troughs. So that's how I remember it. Draw what the above wave would look like if the wavelength were shorter. How would that affect the frequency? Well, if the distance from here to here was shorter, let's say it was from here to here now, it would just mean that it would go like this. And that would mean that there would be more waves in a shorter amount of time. What does that mean about the frequency? The frequency is how often a wave happens per unit of length of time. So if we had more of them, that would mean that it would have an increased frequency because they would be happening more frequently. Okay. And the picture down here would be like tighter wave. It would be like. Okay, number 37. Draw what the above wave would look like if the wavelength were longer. How would that affect the frequency of the wave? So if I were to grab this and stretch it out like that would be a longer wave. So if I drew a picture of it, it would be really long like that. How does that affect the frequency? Well, would there be more waves or less? There would be less because I stretched it out. Therefore, the waves are happening less frequently, and that reduces the frequency. What would that sound like if this was like sound? It would go for a really frequent high frequency, and a low frequency would sound like. Okay, number 38. Which picture would sound travel faster through and why? Sound needs a medium to travel through. What do we mean by that? It actually has to hit particles because it's like a compressional wave. It's energy. And when the energy hits a particle, the particle vibrates and then hits another one and sends the vibration onto the next one and the next one. So it's just a vibration of particles. In these pictures, which would it travel through fastest? It would actually be the second one. Why? Because the particles are closer together and the sound could reach the next particle faster. So it's like in the first picture, it's like but in this one it's like the second one. So closer particles help sound travel faster. Well, you might say, well, then how come I can hear people yelling across the air pretty fast? Well, have you ever yelled underwater? You can hear that fast as well. Every time a particle vibrates, though, it loses a little bit of its energy in the vibration. Therefore, sound won't travel as far when you're dealing with solids as they will with air, because you're losing part of the energy each time it transfers energy. Where would you see conduction, convection, and radiation in the picture on the left? Well, we know that conduction is touching. It almost rhymes. I say it rhymes, and they always say, no, it doesn't, Mr. Maloney. Well, it does to me. Conduction is touching. Sounds pretty similar. Where would you see conduction? That would be when something touches something else. So like this log touching the other log, or the marshmallow touching that. Sometimes the fire is touching the stick right there. Okay, convection. Convection is hot goes up, cold goes down. So this marshmallow right here, it's going to be feeling that convection because the heat is rising. And the last one is radiation. Radiation is the outward movement of energy in all directions, not just sideways or left and right, up and down, spherically, like every direction. The sun is a perfect example. In any direction around the sun, you're going to see the energy radiating out from the sun. So that would be these marshmallows on the side because the energy is going sideways. Complete the energy transformation from this experiment. Use this word bank: chemical, mechanical, radiant. So if we have the sun and it sends energy to a plant, what kind of energy is that? It's radiating energy. So it would be radiant to the plant. Now the plant absorbs the energy and stores it in photosynthesis. It turns it into chemical energy. So that's number 2 because it absorbs water, nutrients, and the sun. And then Jackson actually eats the plant and he gets its chemical energy stored in his body as well. Now Jackson goes and plays baseball and he's running and throwing and pitching. That means he's moving, and that turns the chemical energy in his body into mechanical moving energy for that one. 41. Using the picture on the left, describe how potential energy can be changed into kinetic energy. That's this picture here. Potential energy is when that person has the bow drawn back. How can you change it into kinetic energy or moving energy? Let it go. Then the string goes, and the arrow will start flying. 42, using the picture, just describe how kinetic energy can be changed into potential energy. Well, as you're drawing the bow back, that is moving energy. That's kinetic. But as soon as you stop and you're just resting there, that's energy waiting to happen now. Elastic energy waiting to happen. And that is called potential energy. So that's where the potential energy would be. 43. Hey, this is the last question. Oh my goodness. Identify which picture shows reflection and which picture shows refraction. How are they different? When you look into a mirror, or as I'm looking into the camera right now, your image will bounce back to you. So reflection is incoming, bouncing back, outgoing. It's the bouncing of light, and that would be this one here. See how it hits that, which we call the normal right there. Or no, this is the normal. And it bounces off, and the angles are reflected equally off of the normal. Okay? So that if that angle was 45, that one would also be 45. Equal and opposite angles bouncing off. Refraction is the bending of light. So when you see like a laser being bent through water in that video, or a rainbow, prisms, things like that. Not prison, prisms. It is the bending of light through a medium. So it goes through this lens and it bends the light and refracts off that way.